سعدية شادلي. بشرى.
Okay, can you hear me?
Yeah. Me, I hear you. Saeed, you hear Bushra or not?
Yes. I hear.
Okay, let me share my presentation.
Yeah, Bushra, you have like 15 minutes, okay? And then we'll give occasion, okay, for other attendants, okay, to ask you some questions.
Okay, thank you.
Okay, welcome.
Can you see my presentation?
Yeah, I see it. Yeah, I see it. Yeah.
Good morning. Well, before I begin my talk, I would like to start this presentation by remembering the people who have died due to this ongoing epidemic.
Please, Bushra.
Yeah.
We cannot see the presentation, huh?
Me, I see it, Saeed. Me, I see it.
I see. You see the presentation?
For me, yes. For Saeed, I don't know.
For me, no.
Yeah, for me too. Yeah, I see the presentation.
It's okay for me too.
Please just make your mic inactive, please. Just, okay, to give occasion to Bushra to explain us.
Yes. Now it's okay now.
It's okay now.
Yes.
Okay, we can start.
Okay, thank you, dear professor. Well, before I begin my talk, I would like to start this presentation by remembering the people who have died due to the ongoing epidemic, sharing sympathy with their loved ones, and wishing all those currently sick to be well soon, inshallah. Let me also express my thanks to all those working hard to help us in this time, doctors, health workers, police, and the others. Well, today I'm going to talk about intuitionistic quasi-partial functional differential equation with integral boundary condition with my supervisor Leila Sadia Shadli and my co-supervisor Saeed Al-Milyani. This is the outline of my presentation. I will start with a brief introduction, move on the preliminaries of my research. I will be basically talking about intuitionistic quasi-partial functional differential equations with integral boundary conditions. In this session, I will illustrate the main result of the existence and the uniqueness of intuitionistic fuzzy solution. And finally, I will summarize my work by a small conclusion. In the introduction, I will compare three sets: classical sets, fuzzy sets, and intuitionistic fuzzy sets. Well, let's move in the first part to compare two sets, its classical sets and fuzzy sets. Consider an universe set T which stands for temperature, the cold temperature, the normal temperature, the hot temperature. They are all subsets of universe set T. We define the classical approach as follows. For example, the subset cold is defined by the temperature between 5 degrees centigrade and 15 degrees centigrade. Similarly, we define normal and hot. Well, the characteristic function of one of these subsets, for example, if I choose the subset cold, is equal 1 if an element in subset cold, 0 if an element not in the subset cold. Similarly, for the subset normal and hot. Well, we should notice that 14.9 degrees centigrade is cold, while 50.1 degrees centigrade is normal, implying that the classical set have rigid boundaries. Because of this rigidity, the expression of the word or the expression of the data becomes very difficult. Because for me or any one of us will feel that very uneasy. 14.9 degrees centigrade is cold, while 50.1 degrees centigrade is normal. That is bizarre to have such an approach. In fuzzy set is easy to present them here. How do I do it? Well, this is my temperature axis and this is my membership grade function. How do I define that? Now, if the temperature is around 10 degrees centigrade, it's cold. If the temperature is around 20 degrees centigrade, it's hot. If the temperature is around 30 degrees centigrade, it's hot. For example, if I choose the temperature 25, it's here. it's the temperature can be simultaneously hot as well as normal with membership grade 0.5. For example, if I choose another temperature is 22, it's maybe can here, is the temperature more likely in the category normal. Whereas if I choose 28 degrees centigrade, is maybe can here, is the temperature more likely belong to the subset hot. Well, this is a much nicer way to present our sets. Well, this is how the imprecise data can be categorized in various sets using fuzzy set theory. In classical set, we say only a member in a set. Here we see a member in a set associated with membership grade function. There are many examples to understand, to compare between classical set and fuzzy sets. For example, this example or other example, when we talk about the people who are young, middle-aged, or old, in general, when we talk about the age, another example, when we talk about the tools, there is many examples who can make the same concept, same strategy to understand the difference between two theories. Fuzzy mean in general sense when we talk about the real world. Our expression of the real world, the way we quantify or describe the real world, not very precise. Not very precise, that is the fuzzy. This theory is introduced by Professor Lotfi Zadih in 1965. That is an extension of the classical notion. This is a definition of fuzzy sets is defined as follows by the subset A, where the function mu A defines the degree of membership equals 0, between 0 and 1, and equal 1. By contrast, the characteristic function only 0 or 1. Now move to make the difference between fuzzy sets and intuitionistic fuzzy sets. This example is made by Professor Krasimer by his book. Let be A the subset of all countries with elective governments. We define the percentage of the people voted for the government by the degree of membership. And by definition, the degree of non-membership in fuzzy theory is always 1 minus the degree of membership. It is corresponding for the people voted not for the government. In that sense, it means that fuzzy sets cannot make the value or the data or the information more details. Because the question here arises, how can be categorized the people are not voted at all, or the people make a mistake in votes? We need to categorize this part of people. It is a reason, or that's why the Professor Krasimer at another degrees is the degree of uncertainty. If I choose in this case, the degree of non-membership is the corresponding for the people not voted at all. Now we have the possibility to categorize the last part is the people not voted at all or make a mistake in vote by 1 minus the degree of membership minus the degree of non-membership. This theory is introduced by the Professor Krasimer Atanasov in 1983. That is an extension of fuzzy notion. For preliminaries, I will be mainly talking about the tools I used in my research. The definition of intuitionistic fuzzy set is as follows: is defined by the function mu A nu A, where the function the mu A is the degree of membership and the function mu A is the degree of non-membership, and always the addition between two degrees is between 0 and 1. And we define the degree of uncertainty by this formula. We define the collection of all intuitionistic fuzzy number by these forms, plus verify these 4 conditions. And we define triangular intuitionistic fuzzy number by this form, where the following function define the degree of membership and the degree of non-membership. We define also the lower and upper alpha cut of intuitionistic fuzzy number by these forms. And we define the end point of the lower and upper alpha cut of intuitionistic fuzzy number as follows. And for every alpha fixed in 0, 1, the lower and upper alpha cut of intuitionistic fuzzy number is as follows. And thanks to this alpha cut, we define the following operation is the addition and the multiplication by a real number. And if we have an intuitionistic fuzzy number in IFN, automatically verify this 4 condition. And for inversion, we define these 2 subsets. And of course, these 2 subsets must verify this 4 condition of this proposition. and plus these two functions defined as follows. In this case, these functions define the degree of membership and the degree of membership of intuition sequence number in IFN. We define also the following metric, where the metric space IFN D after n is complete. And in this slide, we define what's mean a function continuous at point t0 is 0 uv0 is satisfy this condition. And here we define what's mean a strongly measurable function if the lower and upper alpha cut of this function are measurable. And here we define the lower and upper alpha cut of double integral. And if we have the lower and upper alpha cut of intuitionistic fuzzy number is equal the lower and upper alpha cut of double integral of intuitionistic fuzzy function, automatically this intuitionistic fuzzy number is the double integral of this function. Now we define the difference between two intuitionistic fuzzy number if there is exists and satisfy this equivalent. And here we define what's mean an intuitionistic fuzzy partial derivative if we have this quantity is in IFN and this difference exists and this quantity equal this limit. In this case, this quantity is an intuitionistic fuzzy partial derivative in IFN. Move on, the aim of this presentation is to establish the existence and the uniqueness result of these models with this integral boundary condition. And this, the solution is equal to function psi in the interval minus r 0 times minus r. And here we define the ingredient of our problem, the function f, q1, q2, neta 1, neta 2, and we define state dependent delay as follows. A solution of our model if B continuous satisfy the integral boundary condition, and if verifies this integral equation in the interval GE times GB and equal the function psi in the times in the interval the interval minus r0 times minus r. And here for the uniqueness of our results, we suppose our function is continuous, satisfy the Leibniz condition plus the condition the contraction. Our model has a unique intuitionistic fuzzy solution. To prove these results, we transform the problem into a fixed point problem. It's clear that the intuitionistic fuzzy solution is a fixed point of the following operator is defined as follows. We should show that operator is a contraction operator, and by using Banach fixed point theorem, this operator has a unique fixed point, which is the intuitionistic fuzzy solution of our model. Conclusion, this work have investigated the existence and the uniqueness result of intuitionistic fuzzy partial functional differential equation with integral boundary condition using Banach fixed point. For future work, we will extend this work in a more general model with local condition and no local condition, and why not to find some application and plus the numerical simulation. And thank you for your attention.
Thank you so much, Dr. Bushra Ben Amin. It's an excellent presentation, an excellent speech. Saeed, do you have some comments?
I have supervised this work.
Yeah, I know. Yeah, I know, but be objective, and if you have some comment, okay, welcome.
Okay, but I think donc if there are some questions about this presentation.
There is someone that have a question about presentation of Dr. Bushra Ben Amin. Good. Bushra, what is the originality of your work? Why do you study? Why do you did this study?
I studied for this step. I studied just the theoretical models. Yeah. I know what you mean, because you know the modelization about this model. In the first step, just I'm read some books about some types of hyperbolic partial derivative equation. It's in the mini modelization of some real model. In fact, yes, I'm hearing you.
Okay, and U and V, this function can mean what in reality? You have this, okay, question number one, U and V.
U and V is a solution of this type of equation. It's the solution. It's the degree of membership. Yes.
But if we want to apply it, okay, in the reality, okay, can represent what?
You maybe it's yeah. This is I respond you on the in first in the first that yeah, this is about the modelization. That's I'm doing the theoretical part, and after we can look for some application to understand more what's yeah, not just only an abstract model.
Good, but for slide number 5, I am not agree with you for your slide number 5. Okay, for the interval of comfort, thermal comfort. Okay, I think you have yeah, this one, yeah, yeah. 15 is not called. It depends on where we are. If you are in Canada, 15 it's okay. It's very hot.
Yeah. This is not general. It is maybe to understand is the rigidity of the boundaries. This only.
Thank you so much. Thank you so much.
Yeah. Thank you, dear professor.
Professor Khouit?
Yeah.
Just a small comment.
Yeah.
We need this concept of fuzzy sets or intuitionistic fuzzy sets to modeling some problem with the uncertainty quantity or imprecise quantity.
Yeah, like wind maybe. U and V can be the wind. Yeah.
Okay.
Good.
Okay. Okay.
Okay, good. Thank you so much, Dr. Bushra. Thank you so much, Saeed also. Okay. Now we go to Abdullah Takbibt. Abdullah Takbibt.
Yes.
Abdullah, you are here?
Yes, I'm here. You hear me?
Yeah, I hear you. Yeah.
Yes.
Yes, Abdullah, you can start.
Just some second.
Yeah.
Please. Do you see my presentation?
Yeah, I see it. For me, I see it. Saeed, you see it?
Yes, it's okay.
For me,
Okay. So welcome everybody in this presentation. So my work entitled solving generalized heat equation by means some generalized fixed point. So I will thank all authors of this work. So Said Madiani and Taqdeer and Mrs. Shadley. So my presentation have the following plane. So first we have an introduction. Second, and we have preliminaries, which I speak about contraction in locally convex and complete space, and the contraction operator in the space X cell. And finally, the generalized evolution problem has application. So the French mathematician Laurent Schwartz has published a result, a theorem result, said that there not exist a commutative, associative, and differential algebra A of U plus and multiplication with the following property. First, the space of distribution. So sorry for this for these notations. So following property that the space of distribution is linearly embedded in this algebra with f equal to 1 is the unity of U. The second, that there exists an operator of derivations linear and satisfying the Leibniz rule. And finally, the restrictions of the law multiplications in space C of U is continued. So some years later, Jean-François Colombo proves the famous theorem of Schwartz by replacing the hypothesis 4 by another hypothesis 4 prime. That's the restrictions to the multiplications in C infinity of U times itself as usual product. So we have here a problem as a motivation. So the problem 1 is an example which shows the importance of nonlinear generalized functions in the solutions of non-partial differential equations. Since Brazis and Friedman showed that the above problem does not allow a weak solution. It means problem 1 has not a solution in distribution set. So we have here the theorems with the hypothesis for prime. So preliminary. Let omega be an open subset of Rn and U epsilon be a family of smooth functions with epsilon as a parameter between 0 and 1. We are to distinguish the following subalgebra. So we have property 1 corresponding to the family of moderate function, and property 2 corresponding to the family of negligible functions. So the moderate families, yes. So the moderate families that satisfy a locally uniform polynomial estimate as epsilon goes to 0. So we define the algebra of Colombo as the quotient of moderate space over negligible function. So the Colombo algebra on a closed half space Rn times 01 is defined in the similar way. The restriction of an element U of this subset to the line t equal to 0 is defined as in property in the relation 4. The space of compactly supported distribution is embedded in this algebra by the convolutions map. So in property 5, since phi epsilon is defined as in the relation 6. So the idea of this work is how to define a mapping between two algebra of Colombo. So how to define a mapping between to algebra of Coulomb. So the first we consider a family of mapping epsilon go to x into x for h x epsilon is moderate and y epsilon is negligible functions. So we consider first that a epsilon of x epsilon is a moderate functions and this difference is negligible. So we can define the mapping A between x into still from x tilde into x tilde as like this formula. So some speed. So from 1 in the previous result, we see that the class here sigma it means the class, and if x epsilon plus y epsilon is another representative of x, so from 2 we have the difference is negligible, and so A is well defined. So now we will give the definition of some definition.
Yes, Abdullah, I don't hear you. You have a technical issue or what?
So I am so sorry for this problem.
No, we don't see your presentation at all. So Said.
Yes, Ibrahim.
Yeah, we can remove to the next one.
Yes.
Okay,
I think yes.
Okay,
Yeah,
okay,
okay.
Abdullah, we'll give you occasion. Okay, inshallah, we will come back to you after. Okay, now we move to Idrisi Said. Idrisi Said.
Yes, I'm here.
Okay, okay, we can start with you.
Good morning.
Okay? Good morning.
Good morning. Okay.
And for Abdullah till Gates, okay, we will give him, okay, after inshallah, okay, occasion, okay, to present.
It's okay for you?
Yeah, for my seat, Dr. Said.
Yes.
Yes.
It's okay. I can start. I
Yeah.
can start.
Yes. Yes. You can
Thank
start.
you. Hello everybody. I'm Idris Said, member of Laboratory of Fundamental and Applied Physics, Faculty of Polydisciplinary, Kadayat University. My contribution in the International Conference on Optimization and Applications, Detailed Stability Analysis and Infinity Performance for Nonlinear Takagi-Sugino Fuzzy System with Time-Varying Delay. The outline of my presentation is divided into 5 parts. I start by introduction, the problem formulation, next main results, the numerical examples, and I will finish by conclusion and perspective. Introduction. The Takagi-Sugino fuzzy system model has been studied extensively in the recent years. It combines the theory of the fuzzy logic and the theory of linear system. It has been shown that the TS fuzzy method provides an effective way to represent some complex nonlinear systems with time delay by using the fuzzy sets and the membership functions. Time delays is one of what is are concurrent in various practical systems such as mechanical systems, chemical systems, engineering systems, networked control systems. And it will know that the existence of the time delays is one of the instability sources and degradation of the system performance, even instability. So, the existence of the time delays causes the poor system performance and the divergence and instabilities. Now we go to the problem formulation. Consider the Takagi-Sugino fuzzy model with our plant rules. Plant rules I. If alpha 1 de t is theta I1 and alpha p de t is theta IP. Then, so conclusion, the TS fuzzy model can be described by these equations, such that x de t is a state vector and 2 de t is a time-varying delay satisfies the two conditions, such as time-varying delay is bounded, HM is a lower bound and HM is upper bound. And derivative, such as D is the upper bound of derivative delay, where the lower bound, upper bound, and D are real constant scalars. Now, Z dot T is given by this equation, is represent a control output. Omega T is a signal disturbance. And phi dot T is a function initial. Finally, the matrices I, EI, E to I, BI, CI, C to I, DI are the constant real matrices with appropriate dimensions. Now, by using a center average diffusivier, the dynamic global of Takagi-Sugino fuzzy system can be expressed as equation 2, such as the mu e of alpha t is the membership functions, and the mu e of alpha t is given by this equality, such that theta eg of alpha g to t represent the membership function degrees of alpha g in the fuzzy theta eg sets. Now we go to the main results. In this section, we present our stability analysis and H infinite performance. Our results established by lemma 1. If there exists matrices positive P, Q1, Q2, Q3, Z1, Z2, and some matrices functions, such that the Flawali matrices inequality holds. That means the linear matrix inequality is negative for a given scalar delta positive, then the previous system 2 is asymptotically stable and satisfies the H infinity performance index. Where omega 1, omega 2, omega 3, omega 4, omega 5, and A are the elements of the previous element. The same phi 1, 2, phi 4 are the elements of the element presented in lemma 1. Now, to demonstrate the previous element, we choose the Flower-Lyapunov-Krasovsky functional VXT and Frey-White matrices, and some techniques are used to demonstrate the effectiveness of our approach. Now, in this section, numerical examples, we present 2 examples to show the effectiveness of our approach developed in this paper. Example 1, consider the TS fuzzy model system 3 with 2 rules and some matrices parameters. The table 1 represents a minimal index gamma for D equals 0.2 and the lower bound equal 0 compared with some literature results, for example, Lin et al., Su et al., Young et al., for different values of theta and the upper bound. So we can see from this table, our results is we obtain the minimum values for index gamma for different values of delta and the upper bound. So we can see that our result is less conservative than the literature results. Now, the examples 2, we consider the system 3 with 1 rule, with the matrices of the system. Similar, the table 2 represents the minimal allowable index for interval, lower bound, and upper bound for D equals 0.3. For example, we take this interval, the lower bound equals 0.5 and the upper bound equals 0.9. We can see that the element presented by UL is infusible, but those presented by our lemma and SUL are fusible, and my result is minimum values for gamma. So we can see also that our result is less conservative. Conclusion and perspective. In this section, the H infinity problem for Takagi-Sugino system with time varying delay is investigated. An appropriate Lyapunov-Krasovsky functional free-weight matrices and the new design methodology are used to obtain new delay dependent conditions in terms of linear matrix inequalities. 2 examples are presented to show the design procedure of the present result and its improvement over existing method. Finally, extend this work to investigate the problem of H infinity filter designed for nonlinear system with time varying delay via Takagi-Sugino model. And thank you for your attention.
Thank you so much, Saeed Idrisi. For me, it's an excellent presentation. I give occasion to Saeed, Professor Saeed Emiliani, if you have comments.
Yes, Saeed Rahim. Idrisi, the coefficient of your matrices or fuzzy or scalar?
The coefficient of scalar is scalar.
Scalar, okay.
Yes, is given the literature results.
Yes, you know, the product between 2 fuzzy quantity is not, we cannot guarantee the stability.
No, our objective is to guarantee the stability.
Okay. Okay. Thanks for your speech. It's very nice.
Just one comment, Saeed
Ibrahim.
Yeah.
Yes. Yes.
Saeed Idrisi,
yes.
when you show us, okay, literature, okay, lean and all, I don't know, table slide number 19. Okay.
Yes, yes.
Yeah, please. We and all. Okay.
Yes.
We and all. Okay. Here you should put year. I would like to see the year.
What?
Yeah, years.
Yes, yeah. Excuse me, yes.
Yeah, year. I would like to see
Yeah,
the year.
Yes.
Okay.
Yes.
And please, okay, we can apply this study in which field?
What you study in?
Yeah, application of this topic. Application.
Slide.
No. Globally. Your topic, globally. What is the application of this topic? Okay, maybe in manufacturing or what?
I study in the. Yes. There is no application exactly.
So why you studied? If there is no application, why you studied?
I study in the academic examples.
Only, but
Yes.
this Said, this
Yes.
one is not it's not theoretical. It's application. You should to have field will we can apply this this topic.
Yes. Thank you.
Yes.
Okay, thank you so much.
Thank you so much. I don't
Move
want
to
this.
محمد العمري.
Okay.
Yes. You can start.
I will share. Yeah, okay, I will share my screen. Okay, you can see.
Yes.
Okay, I see it. Yeah. Okay, good.
Okay, just a remark. I'm not Omari. I am Idris Bakhdash. I will present this presentation in collaboration with Mr. Mohammed Omari and collaboration with my director thesis, Mr. Professor Said Miliani, and co-director thesis, Madam Professor Sadia Shadi. So as I see, my name is Idris Bakhdash. I'm a PhD from Sultan Moulay Slimane University, Faculty of Sciences and Technologies. I'm a member of Laboratory of Applied Mathematics and Computing Sciences. So my talk is about quasi-fractional neutral equation. My talk will be in 6 parts. In the first part, I'll give you the motivation problem. Then in the second, I'll present some definitions and introduce the necessary results which will be used through the paper. The other sections will be booked to the theoretic study of a problem and illustration by an application. So this presentation is devoted to a class of nonlinear quasi-neural fractional differential equation defined as follows, with GHD is denoted the capital fractional generalized derivative of the function if f and g are two functions which satisfy some assumption that will be specified in the next section. We denote now E1 the class of function defined as follows with these 4 properties. We defined the alpha cut of a fuzzy number with this formula, and we can write the alpha cut like a fuzzy an interval with lower alpha cut and upper alpha cut. The multiplication by a scalar is defined as below. We recall also the definition of distance between two fuzzy elements. So the space E1 with the distance D is a linear normal space with the norm is defined as you see in the screen. The norm is the distance between the fuzzy element and 0. We defined also the product between fuzzy elements in terms of alpha cat with this equality. The generalized Hikuhara difference of two fuzzy number is defined by these properties. We have two cases, case 1 or case 2. The generalized Hikuhara derivative of fuzzy valued function is defined as follows: is the limit we defined also the differentiable of a fuzzy valued function. We suppose that we have the upper alpha cat and lower alpha cat both differentiable at x0. We have two cases. If is type 1 differentiable at x0, if we have this equality, or we say that if is type 2 differentiable at x0, if we have this second equality. We record also the Riemann integral, the fuzzy Riemann integral of a fuzzy valued function. And we say if f is GH differentiable with no switching point in the interval AB, then we have the integral of a fuzzy valued function can be written as a generalized Hikuhara difference between two fuzzy elements, if B and if A. We go now to the generalized fuzzy fractional derivative section. Let's now f a fuzzy valued function. We will define the fuzzy Riemann-Liouville integral of fuzzy valued function as you see in the screen now. With this function is Euler gamma function. This function. We recall also fractional derivative in capital sense is given by this form. Now, if we have a fuzzy valued function, if is it a type 1 differentiable at a point t0, then the fractional derivative of this function is also type 1 differentiable, and the same thing for type 2. If f is type 2 differentiable at the point t0, then all the fractional derivatives are differentiable of same type, type 1 or type 2. Now we turn on the fuzzy semigroup. So a family of a fuzzy linear operators from E1 into itself is a fuzzy strongly continuous semigroup if they satisfy these three conditions. Condition 1, 2, TS plus equal the product, and the fuzzy valued function G defined by Gt equal this quantity is continuous at T0, and we have this limit. So we define also fuzzy strongly continuous semigroup on E1. So if we put the operator defined by limit, whenever this limit exists in the metric space defined early, then the operator A defined on dA is called the infinitesimal generator of the fuzzy semigroup. So there we have a very important theorem that we take the relation between the fuzzy semigroup and the crisp semigroup. If A is the infinitesimal generator of fuzzy semigroup T, then we have E1 defined by GA. G minus 1 is also the generator, the infinitesimal generator of crisp semigroup defined by GT G1 G minus 1. So this is very important results show us the relation between a crisp semigroup and fuzzy semigroup, with G is an injection from E1 into a Banach space. An integrated fuzzy semigroup is a family of a bounded linear operator on E1 which satisfy the following properties. Now we go to fuzzy fractional neutral problem, our problem. In this section, we consider the existence and uniqueness of the fuzzy solution of nonlinear fractional fuzzy neutral functional equation, as we talked in the beginning, where we have this position. We consider that this semigroup is integrated semigroup, and F and G are defined from D times E1 into E1, nonlinear continuous functions, and satisfy a global Lipschitz condition. So if we have our problem, then we can guarantee the existence of a solution which is unique if we have this quantity, if we have this inequality. So our problem has a unique solution on E1 if we have this equality. So now we have an application. We consider the nonlinear fuzzy neutral functional differential equation given by this. You can see it in the screen. We have the initial value. The initial value is a fuzzy quantity if it's in E1. So we're the upper alpha cut of xt plus r plus h is positive, and our operator A is a triangular fuzzy number defined by this alpha cut. So we have the alpha cut of the first quantity and the second quantity. Then we can show that the problem has a unique solution whenever this quantity holds. And I'd like to thank you for taking time out to listen to my presentation.
Thank you so much, Idris Dash. It's an excellent presentation. Said, have you some comments?
There is, yes, it's a very good the speech by
Idris.
Ouais. Okay, donc no comment.
Thank you so much. Said, Idris, what is novel in this study?
What?
Yes.
Novel. What is the originality of this work?
Yes.
Novel.
We, as you see, let me show you. The novel is we are the first.
Good. I like this. We are the first. It's okay for me. Okay. Thank you.
Yes. No. You hear me? You can hear me?
Yeah, I hear you.
Yes, please.
In the literature, we have this equation, this neural fractional equation in the crisp case, with the initial condition is a crisp. There is the solution of this equation in the literature on the crisp set. Our aim is to take risk if we can find a solution of this equation, but using the initial value is a fuzzy element.
Good.
That's our novel.
Good.
Hey, Ibrahim?
Yes.
Yes, it's the first work when we combine with the fractional derivative and and fuzzy numbers.
MashaAllah, mashallah, it's good.
Okay.
Good. Okay, now we can go to Basur Mustafa.
Yes. Hello.
Okay, Basur.
You see my presentation?
Yeah, I see.
Yes.
For me, okay. Go.
I will present a numerical method to solve a problem of generalized eigenvalue. The title of my presentation is Solving Pencil Problem Generalized using Cholesky-like decomposition for skew Hamiltonian matrix. The plan of my presentation is first, introduction, second, Cholesky-like decomposition for skew Hamiltonian matrix, third, numerical example. We present a new method for solving skew Hamiltonian generalized eigenvalue problem. The problem is in the following form. The first matrix is skew Hamiltonian matrix, and the second is Hamiltonian. We consider the matrix J in this following form. A matrix M is skew Hamiltonian if Mj equal M, where Mj equal J transpose M transpose J. And a matrix N is called Hamiltonian if Mj equal minus N. A matrix S is symplectic if Sjs equal I to N. The matrix M in the following form, its G transpose is given by Mg in this following form. And every skew Hamiltonian matrix M is of the form where G and F are skew symmetric. We construct a method for solving pencil problem I minus lambda b times v equal 0. We transform this skew Hamiltonian pencil to a standard Hamiltonian eigenproblem each v equal lambda v. This transformation is obtained after decomposing B as R transpose JR. The Hamiltonian matrix H is given by J transpose R minus transpose E R minus 1. It is known that any non-singular skew-symmetric matrix has as decomposition of the form B equal R transpose JR. The real matrix M equal J transpose times B is skew Hamiltonian and have the decomposition J transpose times B equal R JR. There is an equivalence between the skew symmetric and matrix skew Hamiltonian. Instead of factorizing the matrix B equal R transpose JR, we factor the matrix M equal R J R. By factorization R J R of skew Hamiltonian matrix J transpose B, we obtain H W equal lambda W. The matrix H is Hamiltonian. We verify that the M equal R J R, and we have mg equal m. We that M is skew Hamiltonian matrix. We will write the matrix M and R in this base. We have M and R. MEG, the element of the matrix M, and REG, the element of the matrix R. The matrix R is all written in this following form. We set L equal R J to simplify the calculation for R J R. Donc we calculate L J. We calculate Lj. We obtain MEG element of the matrix M skew Hamiltonian matrix. Consequently, that's an algorithm which gives the Cholesky-like decomposition for skew Hamiltonian matrix. We have construct element of the matrix M. We give a numerical example to apply this method. We present computed eigenvalue that solve the pencil problem in the form. We transform the pencil to standard Hamiltonian eigenproblem, each V equal lambda V, by decomposing this key Hamiltonian matrix RJR. The Hamiltonian matrix H is obtained by this form, this following form. Eigenvalue problem of this type is property that all eigenvalue appear in the quadruple. And we have this spectrum is symmetric because the matrix M is skew Hamiltonian matrix. Mg equal M. Donc this spectrum is symmetric with respect to the real and imaginary axes. We used MATLAB to program the algorithm. Thank you for your attention.
Thank you so much, Basur Mustafa. Thank you for this presentation. Mr. Saeed, this is Saeed. Have you questions or comments, please?
Yes. See, Basur, what you say by generalized problem?
generalized the matrix is skew Hamiltonian and Hamiltonian.
Okay.
Donc, je m'excuse, je parle en français.
Oui, vas-y, il n'y a pas de problème.
Au lieu de traiter un problème symétrique, antisymétrique, oui, j'ai traité un problème, ce qui est hamiltonien.
Parce que le mot généralisé, donc les problèmes généralisés ou bien les solutions généralisées, donc il y a toute une théorie là-dessus. Donc c'est la théorie des fonctions généralisées, là où...
Oui, bien sûr, parce que j'ai pas utilisé la base canonique pour écrire les bases, donc j'ai écrit les matrices dans une base OI où j'ai transposé. OI appartient à R2N fois 2.
D'accord.
Parfait.
Toi, la parole.
Vas-y, si vous avez des questions, vous, monsieur.
C'est bon. Oui, c'est bon, c'est Abdrahim.
Vas-y. Bassour.
Oui, monsieur.
Ok, pour moi, ok, parfait. Moi, je cherche toujours l'application. Moi, je suis issu d'une école d'ingénierie, je cherche toujours l'application. Skew Hamiltonian matrice, on va l'appliquer où? L'application. Fil غادي نطبقوها.
Oui,
de réalité.
C'est dans la factorisation, parce que pour trouver les éléments dans la matrice M, donc pour simplifier les calculs, donc j'ai créé les matrices dans la base OI où j'ai transposé, donc ça pour simplifier les calculs. Parce que si on travaille dans la base canonique, donc c'est difficile de faire les calculs. Donc je passais de symétrique, antisymétrique à ce que Hamiltonien, c'est pour simplifier les calculs. Oui, bien sûr. Oui, pardon. Et pour, oui, bien sûr, là, le problème est sur la forme suivante, A moins lambda B fois V égale 0. Donc, après les transformations, j'ai transformé le problème à un problème standard. Bien sûr, avec des... Donc, j'ai remplacé la matrice B par R transposé GR. Mais pour la factorisation, au lieu de factoriser R transposé GR, j'ai factorisé RGR.
C'est Bassour.
Oui, monsieur.
Oui, je crois, donc la question de monsieur Ibrahim, donc c'est bon, l'application de ce que vous venez de présenter. Il faut, je crois, essayer de chercher des problèmes physiques, ou bien pour résoudre certains problèmes physiques, donc où on peut appliquer donc votre résultat. Donc, il est l'apport donc pour la résolution des problèmes réels.
Donc le problème, c'est un problème de physique, ça, c'est un problème. Donc sous cette forme-là, donc on a une matrice A moins lambda B, avec A iscu hamiltonien.
Quel type de problème physique?
Voilà, type de problème, voilà. Parce que vous n'allez pas présenter comme ça, vous n'allez pas dans la société pour dire, voilà, J moins K, la matrice, il ne connaît même pas la matrice. Donc, comment vous allez faire pour vendre votre résultat?
Mais dans les exemples numériques, j'ai traité des problèmes qui existent dans des autres papiers, bien sûr.
Ok, parfait. C'est quoi la dernière question, mais vite fait, hein? C'est quoi l'originalité de ce travail? شنو هو الجديد في هذه الخدمة ديالك؟
Bien sûr, après, pour la factorisation, pour la factorisation de la matrice M égale RGR, j'ai calculé la norme de Frobenius, M moins lambda RGR.
N'importe qui peut faire ce calcul, c'est pas quelque chose de...
Mais j'ai comparé avec les autres résultats déjà existants. J'ai comparé l'erreur.
Ok, parfait.
Pour moi, j'ai trouvé donc 10 à la puissance moins 14.
Parfait, c'est bon. Merci beaucoup, Monsieur Bassor. On passe à Monsieur. Merci beaucoup, Monsieur Bassor. Hein.
Merci.
Ok, parfait. Monsieur professeur Saïd.
Oui, oui, c'est vrai.
Donc, on revient vers Monsieur Abdallah Tagbib. On lui donne l'occasion.
Je crois, oui, mais je crois qu'il a un problème de connexion. C'est pour cela donc il n'arrive pas.
On va vérifier avec lui. On va vérifier avec lui si
D'accord.
c'est OK. Sinon, on passe à la délibération. Donc,
D'accord, d'accord, c'est Ibrahim. OK.
Abdelilah Tagbibt, are you okay? Are you ready? Ilah, Abdullah Tagbibt. Do you hear me?
Shuaib.
Okay, Said, I think Abdullah Tagbibt has a problem, a technical problem. Okay, thank you so much. We can now close the session.
Okay.
Thank you so much. And we can. C'est Saïd, donc on passe au privé pour délibération, ok?
Oui, d'accord. Oui.
Ok, donc merci à tout le monde. Thank you so much for all of the attendance, okay? And we will close this session. Thank you so much. Assalamu alaikum.
Thank you so much.
Thank you.